All right, what up, guys? Welcome back. So today I want to talk about partition functions. So why is it so important? And if you're being provided with an ensemble, which I explained what it is, how to write the correct partition function for it, and from this partition function, how can you obtain other thermodynamic functions? So let's get started. So the key thing in thermal, I just want to emphasize this, is to find the correct partition function for a system. So this is the equation that currently we know, but sometimes I find it confusing. Like, where does this exponential come from? Like the beta term, like why is it like this? So basically, right now we have to think about it as a sum of the exponential of the beta term times the energy at this each energy level k. So k is for each index for the specific energy levels. And so why do we need it? And where does it come from? That's the answer we want to find today. So it all comes from probability, right? So let's think about if we all have the same stuff, let's say circles. And so you have five of blue, one of yellow. So in this case, probability is really related to how many of something you have, right? So the probability I'm gonna find this yellow here is going to be 1/6. And what about blue is gonna be 5/6, right? So that's where degeneracy comes in, the omega term. So if everything is the same, how many of them do you have? But in other cases, we have to count into other influences. So let's say this is not a circle anymore, it becomes a square. Well, we can still count it in the similar fashion, but we just have to um, like make the equation take account for the different like other factors here. So how do we find the probability we can find in a system in the energy level of k, which is what's going to be required in in the partition function? Well, let's start with what we did. Is the most straightforward thing is the canonical ensemble. So canonical ensemble means you have a closed system uh, with constant temperature. So that means the number of particles cannot change. It's always n over here. But you can get energies across the barrier, so the temperature will be the same. So the ensemble basically is uh, for this n number of molecules because they have energy and they're constantly moving around, they're constantly bouncing to each other, so the energy are constantly changing. So you can imagine that at this one moment, you take a screenshot, and then at the second one, they're gonna look different. And if you count for all of them, this is an ensemble. So basically means a collection of microstates. So what do we know about the energies of each of these particles in this canonical ensemble? Well, we know several things. So first thing is that the energy for the probability um, to have the particles at different energy levels are not the same. So if imagine you have like a bar going from low energy to high energy, you probably will have like just intuitively you're gonna have a lot more particles in the lower energy states than the ones in the high energy state, right? So we can say that the higher the energy state, the more unlikely the particles will be in that state. And also from another perspective, that tells you that this probability of the particles being energy EK depends on this energy level. But however these energy levels are, the sum of them will always be one because all the possibilities summed up will be one. So from these, how can we determine what is the probability that a system is at uh, at the energy state EK? Well, let's do a very simple derivation. So imagine you have a bath, so it's a heat reservoir, and you have two smaller systems. So one's called EA, one's called B, And EA, in the system A, you have energy EA. In the system B, you have energy EB. And let's denote two things. So the PAEA will be the probability of finding the system A in one of the microstates with energy EA. And similarly for PBEB, is the probability of finding system B is in a microstate with energy EB. And now, what the change I'm going to do is I'm going to bring these two parts into contact with each other. So there's no energy change, there's no particle exchange, but they're just being here together. So we denote that the PA plus B will be the probability of finding the system A and B in one of the microstate with energy EA plus B. Well, now the interesting is that we know this energy, the sum of these energy, so by putting them together, will equal to the ones that are separate. And because we know the probability, the sum of them, because PA plus B, EA plus B will equal to, we substitute the EA plus EB in here, they actually equal to the joint probability, because however you're simply putting two things together, so individually they should still be the same. So that tells you that the probability of A is independent of the probability of PB. So now we take the second part of this equation and we call this equation 1. And if we differentiate it with respect to EA, then the left-hand side will be a partial derivative with respect to EA. And the right-hand side, so this part is not a function of EA, but this is. So you hold this constant and you take the straightforward derivative for this. But you can't just directly, because it's partial derivative, so you cannot just directly take it. You have to use the chain rule. So this term becomes the derivative of PA plus B of EA plus EB over with respect to EA plus EB, and the derivative of EA plus EB with respect to EA, which is the value of 1. And this will equal to the right-hand side of this. And now what's going to happen, so this should be EB. What's going to happen if you take the derivative for EB? Well, it's actually going to be the same. Let's do the same process. So you take the derivative of EB, you hold the PAEA constant this time. And you take derivative of this part, and we do the chain rule, and the second part will still be this 1. So that means these two are exactly the same. The derivative of PA plus B, EA plus EB, with respect to EA plus EB. But they actually equals the different terms. So now we can build a connection between these two terms, and they are the same. So let's bring these two terms to here so we know these two are the same. And let's just denote this derivative P prime A EA to make it easier. So if we reorganize this thing by putting PB to that side and PA to that side, we get this relationship. And what's amazing about this equation is that on the left-hand side, it's all about A, and on the right-hand side, it's all about B. So that means this side has nothing to do with the EA, and this side has nothing to do with EB, sorry, the other way around. So that means this must be equal to a constant, which is, we're going to denote negative beta, or later on we'll find it's going to be negative 1 over kBt. So let's just say, take the first half, so this equals negative beta, and we're going to move the PAEA to the other side. So PAEA, remember how we got EA, is just make this part simpler, so we write a whole part of it, equals to negative beta times PAEA. And if we move PAEA, because this is a differential of PAEA, and we have PAEA over here, so we move this, make it 1 over PAEA, dPaEA will equals to negative beta dEA. And now we take the integral of this. This becomes the ln of PaEA equals to negative beta EA plus C. And because we know that the ln of AB equals to ln A plus ln B, so we know that when we take e to the power of ln equals to e to the power of this, we can actually bring this to the front of it. So make it C times the exponential of negative beta EA. So if we generalize this, we take the A away, we get the probability of finding an ensemble in the energy E will equals to some constant C times the exponential of negative beta E. And this is what we're going to build our partition function on. And actually, that's why in our partition function over here, we have this exponential term. So we know that the partition functions, the sum of all of the probabilities will be 1. And we know the probability has this expression. So we can set it up. So the sum of them will equal to 1 will equal to the sum of C times exponential negative beta E. And we take the constant out and becomes C times the sum of exp negative beta E. So if we move the sum to the left hand side, so make a 1 over of that, we get this equation. And that's how we build our partition function. So the partition function is 1 over C, 1 over this constant, and is which is also a constant, and equals to the sum of the exponential of beta ek. And we know that. So our original goal was to find the probability of finding a ensemble in the energy Ek, and so that will be the probability of E over the sum, which will be 1, right? So that gives, what does that give you? Well, that gives you 1 over Q, right? So this is Q times the exponential of negative beta E. So from here, I just want to, so with this probability, so what can we get out of it? Well, so the partition function, so the meaning in its German form means the sum of state. And from this partition function, we can get the energy of a system, where we can build from that to get all other thermodynamic functions. So I want to demonstrate this with an example. So see here, let's consider a system of one particle that can assume energy levels of 0, epsilon, 2 epsilon, 3 epsilon, and epsilon are greater than 0, so it's positive, with degeneracies of 1, 3, 3, 1. So that means you have one possibility of having energy levels of 0, and 3 possibilities of having energy of epsilon, 3 cases having possibility of 2 epsilon, and 1 case of having energy 3 epsilon. So what is the partition function? Well, we just use this form. So we know that the partition function is the sum of the exponential of negative beta E. So if we write the sum, so there's one case, so 1 times e to the power of negative beta times the energy in this is 0. So this terms becomes 1. And 3 cases of the exponential of negative beta times energy epsilon. And 3 cases of exponential of negative beta times 2 epsilon. and one case of the exponential of negative beta times negative 3 epsilon. And if we organize this, we'll find actually this term equals to 1 plus the exponential of negative beta epsilon to the power of 3. And I just want to, another thing I want to point out is this coincidentally, this equals to the result as when you have 3 identical particles with the energy level 0 and epsilon. So with this, how can we find, now we have the partition function, how can we find the average energy of E of this system? So this is the partition function, and we know the E is the average of all energy states. So that will be the sum of the energy state times the probability you have of this energy state, right? And we know that the second part equals to 1 over Q times exp negative beta ek times ek. So on the right hand side, we find that the E term in this theory can be generated by differentiating the negative exp negative beta ek by beta. So through this method, we can find, you see, if we take this term, take the right-hand side term, and differentiate it with respect to, so if we, so take this term and differentiate it with respect to beta, we get negative the sum of ek, because the exp, if we take respect to beta, you get negative ek times the exponential of negative beta ek. So now we can rewrite this E as negative 1 over Q, the negative comes from here, times the derivative of K, the exp negative beta ek with respect to beta. And this is also Q. So we can rewrite as negative 1 over Q times dq d beta. And this is also, if we organize this will be also negative of the ln of the partition function with respect to beta. So in our case, the ln Q is ln 1 plus e to the power of negative beta epsilon to the power of 3, which is negative 1 over 1 plus e beta epsilon to the power of 3 times 3. You take this, so you bring this to the top, you differentiate this term separately, so it's 3 times this term to the power of 2, and now you differentiate the e to negative beta term, so negative epsilon times e to the power of negative beta epsilon. So the 2 and the 3 cross out, so you're only with this term to the power of 1 at the bottom, and you have the negative crossed out, you have the 3 epsilon times e to the power of negative beta epsilon. So this should be on the power. And if you divide the numerator and the bottom part, you get 3 epsilon over 1 plus e to the power of beta epsilon. So this is how we can get the average energy from our partition function. And with the function E, we can get from the classical relationships of starting, we can get all of the stuff. So for example, we can get ds, the value for S, entropy, and pressure from this relationship. So that's what I want to emphasize, is how we get to know where the partition function comes from and how we can use it to derive the function of E. And from that, we can get other thermodynamic functions. So I hope this is helping you guys, and see you in the next one.